Hi, welcome to 8.1. We're doing law of sines and law of cosines. So the use of law of sines, law of cosines, we use law of sines and cosines to find the missing components of a triangle. You might need an angle, you might need a side length. If you know parts of the triangle and not necessarily a right triangle, that's key to this. Most of the times they aren't going to be right triangles. We can often use one of these two laws in order to find the missing parts. Sometimes we'll use both laws together. The law of sines is used if we know either two angles and a side, maybe angle, angle, side, or angle, side, angle. This right here means two angles and the side not between them. We could find the third angle by subtracting from 180, subtracting the sum, or angle, side, angle. Or if you know two sides and a non-included angle, the side-side angle situation. The problem in this last case for the side-side angles, we have the potential to have two types of triangles, or two triangles called the ambiguous case. So it's possible, and we'll see that on our next page, the different situations. The law of cosines is used if we know two sides and the included angle, that's side, angle, side, or all three sides, side, side, side. In the law of cosines, there's only one possible triangle, and so there's no possibility of multiple triangles, no ambiguous cases. So the law of sines, for the law of sines, we'll reference this triangle, and I'll tend to draw this triangle right here. And just kind of this shape won't be to scale. You know, B might be 20 degrees in one case, it might be 100 degrees in the next case, just to get a visual of the relationship of what's happening. Now, the capitals are the angles, and the little letters are the sides opposite those respective angles. So, angle A, side A, angle B, side B, angle C, side C. So sine of A, sine of angle A over side A is equal to sine of angle B over side B, which is equal to sine of angle C over side C. And that's the law of sines. Let's look at example 1 here. Solve for the remaining angle and the sides of the triangle. So we know A is 60 degrees, B is 40 degrees. Here's my A at 60 degrees. Here's B at 40 degrees. And then down here is C. Over here is side C, here's side A, and that's 2. And here's side B. We don't know what B is or C. Or angle C. But we could find angle C very easily. Because A and B, A is 60, B is 40. So 60 degrees plus 40 degrees is 100 degrees. So C would be 180 degrees, the sum of all the angles in the triangle, minus 100 degrees, which is 80 degrees. So now we know all the angles and one side. We could find the remaining two sides. To do that, I'm going to start with the one that we know. We know the angle for A and the side length for little a. So we could say sine of 60 degrees, that's for A, over 2 equals sine of 40 degrees over B, little b. Now, a couple ways we could approach this to solve it. We can cross multiply, we can flip both sides. There are really a lot of options here. If we flip both sides, we'd have 2 over sine 60 degrees equals B over sine 40 degrees. So that B equals 2 times sine 60 degrees, 2 times sine 40 degrees divided by sine 60 degrees. So when you're doing this, make sure your calculator's in degree mode. And B works out to be 1.48. Addressing that for just a moment. Side A is 2, side B is 1.48. Angle A is 60, angle B is 40. So angle B is smaller than angle A, and side B is smaller than side A. I hope you see that relationship. Now let's get C. We start off with what we had originally, sine 60 over 2, what's given. We could use a sine 40 over 1.48, but there's round-off error in this, and we'd propagate that error if we continued using that value. Sometimes we have to, but in this case we can go back to what we started with. So sine 60 over 2 is equal to sine 100 degrees over C. So 2 over sine 60 degrees equals C over sine 100 degrees. So C equals 2 times sine 100 degrees over sine 60 degrees, and C equals 2.274. So for this triangle, the missing parts were side B is 1.48, side C is 2.274, and angle C was 100 degrees. Okay, so that's our first triangle. Now we'll look at the second one here. We have B is 120 degrees, C is 40 degrees, and little b is 6. So let's find angle A first. So A is going to be 180 degrees minus the sum of the other two. So A would be 20 degrees. Now we need little a and little c, so start with getting little a. We know b, so sine of 120 degrees over 6 is going to be equal to sine of 20 degrees over little a. We flip both sides, 6 over sine 120 degrees equals a over sine 20 degrees. So a would be equal to 6 times sine 20 degrees over sine 120 degrees. So a would be equal to 2.37. And let's get side C. So sine of 120 degrees over 6 equals sine of 40 degrees over C. The angle C was 40 degrees. So 6 over sine 120 degrees equals C over 40 degrees. C equals C over sine 40 degrees. So C equals 6 times sine 40 degrees divided by sine 120 degrees. So C would be 4.45. Now from this problem we had to get angle A, and that was 20 degrees, side A, which is 2.37, and side C, which is 4.45. Now for the last one here on this example, we have A is 40 degrees, little a is 4, and little b is 4. So we have an angle and two sides. And so might get a little stressed about this, and we haven't really gone, we're going to go into a second into more detail about how to do these type of problems, but we don't have to treat it like a side angle situation because of the following. I'm going to draw this one a little bit different than I drew the others. A is 40 degrees, little a is 4. B is, any guesses there? Little b is 4. So when you have two sides of a triangle that are the same length, what you have is an isosceles triangle. And the base angles are the same. If you want to look at law of sines, if you said sine of 40 degrees over 4 equals sine of b over 4, it's pretty natural to conclude that b must be 40 degrees. So now it's a matter of determining c. C would be equal to 180 degrees minus 40 degrees plus 40 degrees, which is just 100 degrees. So here I'm putting C up on top. A little bit different than what we have been doing. My point was to show that these two sides are the same, to give it more of a standard look for an isosceles triangle. Now, sine of 40 degrees over 4 equals sine of 100 degrees over C. So we have 4 over 40 degrees, let's do that again, over sine 40 degrees equals C over sine 100 degrees. So C equals 4 times sine 100 degrees over sine 40 degrees. And so C is 6.13. So from this we found angle B to be 40 degrees, angle C to be 100 degrees, and side C to be 6.13. Feel free to pause there. Now we're going to talk about the side-side angle variations. When you know two sides and an angle that's not between them, there are different things that can happen. We have cases where there's no triangle possible, where there's one triangle possible, and there are two triangles possible. Okay. Now alpha is the same thing as A. We can call that A if you want, capital A. Let's say that A is acute, less than 90 degrees. And we have the case that side A is between 0 and H, or H is the height of the triangle. And this is the height. It's perpendicular from the base to the vertex opposite it. That's the height of a triangle. And here's our little a. Well, if little a is going to be less than H, it's not going to be enough to come down and connect up. You don't have a triangle. There's no triangle possible in that case. We call this A here. There's no triangle possible. Okay. The second case, it's acute still. A equals H, that is, A is equal to the height, that's not hypotenuse, the height here, the perpendicular to the height. Well, you have a right triangle. That's a right triangle. So in this case, if this is your A, this is your B, and this is your C, here's little c, here is little b, and there's your A. So A equals H, and H is defined to be, this side is defined to be, well, sine of A is opposite over hypotenuse. So this is going to be C times sine of A. That is A, little a then, as well. So if A equals H, you have a right triangle, there's one triangle possible. Now comes the most challenging case, is the ambiguous case. I'm going to scroll this up so we can work on this a little more. We'll see this case when we do example 2, part B. Now this is the only case where you could have two possible triangles. Then you'll see this on example 2B. Okay, in this case we have A is going to be bigger than the H. Here's our H. A is bigger than H, but smaller than B. So again here's the H, here's A, here's B. A is bigger than H, but smaller than B. In that case, now given that capital A is acute, we don't know about B. We don't know if this angle B is obtuse as in this case or acute as in this case. We don't know. All we know is that B is more than A. And given that angle A is acute, angle B could still be acute. It could be acute, it could be obtuse. We don't know. We have to go for both cases. Consider both cases, and we'll see this play out on example 2B. And the third case is where A is definitely bigger than B. And a better drawing for this would have been something like here's your A, here's your B, and then here's your little a, here's your little b. A is definitely bigger than B. So I'd drop that one out. And we'll see this type on example 2A. Now when we get to obtuse, there's either no cases possible or one triangle possible. So if we know it's obtuse, our angle is obtuse, so here's our A down here, it's obtuse. If A is less than B, that means this side is not going to be long enough to connect up. Therefore, there's no triangle possible. Let me scroll this up. In our last case here, this is more common for the obtuse. That previous obtuse case is not very common. We have angle A is obtuse. Side A is bigger than B, and that would make sense because being the biggest angle should be the biggest side. Here's your A, here's B, here's C. A is bigger than B. Angle A is bigger than angle B. So there's one triangle possible. So let's go ahead and do some examples with these, and maybe we'll see this a little clearer. Okay, B is 80 degrees, A is 2, B is 6. So if you notice this, B, here's the angle, here's the side opposite the angle, and here's the other side given. Well, we know this must be acute. We have to go with acute because this side's smaller than that side. So its angle that's opposite must be smaller. So here's B, and it's 80 degrees. Here's A. We don't know how big A is. Here's little a, and that's 2, and little b, that's 6. Side C, and little c. So using law of sines, sine of 80 degrees over 6 is sine of A over 2. That means that sine of A is equal to 2 times sine 80 degrees over 6. So that A would be arc sine or sine inverse of 2 times sine 80 degrees over 6. And leaving the calculator in degree mode would give you A being 19.16 degrees. So immediately we can find C. C is 180 degrees minus 80 degrees plus 19.16 degrees. That gives us C being 80.84 degrees. So we have A is 19.16 degrees and C is 80.84 degrees. Now we have to find side C. So we'll go back to law of sines. We'll go back to the first known relationship, sine of 80 degrees over 6 equals sine of 80.84 degrees over C. So we're going to flip both sides. 6 over sine 80 degrees equals C over sine 80.84 degrees. These are pretty close in size, so C is going to be pretty close to 6. So that C equals 6 times sine of 80.84 degrees over sine of 80 degrees. And C is equal to 6.01. And those are the missing sides and angles, or missing side and angles. Okay. Let's scroll this up. I need to spend some time on B. So here we have angle A is 60 degrees. That is acute. Side A is 3 and side B is 5. Let me try to draw a triangle here. So we can have the case where this is A at 60 degrees. Little a is 3. Here's B. We don't know how big that is. Here's C. But I drew B to be acute. And here's little b is 5. Okay. So that's one possibility, and then the other one would be, I'll draw it down here. Here's A at 60 degrees. Here's B. Here's little b is 5. Maybe I should draw that a little differently. Maybe I should draw it like this. That. No, that's not going to be quite right. Okay, I'll stick with what I had. Little a is 3, and here's C. Okay, then we have our little a is 3. This is not drawn to scale because this, but I'm trying to accentuate or exaggerate the point that B is obtuse here. Here's our C and little c. Okay, so let's find B. Sine of angle B. Sine 60 degrees over 3 equals sine B over 5. Okay, so that means sine B is equal to 5 times sine 60 degrees over 3. So sine B is equal to 5 times sine 60 over 3. I'll get my calculator for that one. Five times sine 60 divided by 3. My mode is radians. So go to degree mode now. Put this in the calculator, I get 1.44338. So right there, red flags go up. Why? Because if I do sine inverse of sine B equals sine inverse, or arc sine, of 1.4438, then B equals what? Well, 1.4438 is not in the domain of arc sine. It's not in the range of sine. Therefore, this is not possible. So we could stop there. So if you ever have that case that it turns out your angle is going to be sine of an angle, is going to be something bigger than 1 or less than -1, you can stop. This triangle is not possible. The issue is, because this is 5, it's just too big. That means we're having something like, here's 60 degrees. We don't know what B is. We know that this is 5, and we know that this is 3. It's not going to make it down there. So it's just not a possible triangle. So this is really probably more, instead of that third or fourth case, this is the, so the third case is probably more resembles the first case. Okay, let's go on to C then. So C is 42 degrees, angle C is 42 degrees, angle B is 9, or side B is 9, and side C is 3. Okay. Now, sine of 42 degrees over 3 is sine of B over 9. So sine B is equal to 9 times sine 42 degrees over 3. So sine B equals 3 times sine 42 degrees. Sine B is what? Three times sine 42 degrees. 2.00739. Again, we had the same problem as part B. We're producing something too big, so we have a triangle that's not possible. If you went the next step and said arc sine of sine B is arc sine of 2.00739, that's not in the domain. So we can stop there. Let's go on to law of cosines. This one works better. Given a triangle ABC with sides labeled conventionally, as we saw earlier, the following are all true. A squared is equal to B squared plus C squared minus 2BC, times cosine angle A. So I want to point out here, side A, angle A on the cosine. B squared is A squared plus C squared minus 2AC cosine B. So this B, cosine B, that's an angle B versus side B. And then C squared equals A squared plus B squared minus 2AB cosine C. See that relationship? Notice the A squared B squared, there's an AB, A squared C squared, there's an AC, B squared C squared, there's a BC. Strategy for solving the side angle side case. Step 1, find the side opposite of the given angle by law of cosines. Then the second angle, find the second angle, the angle opposite the shorter of the two given sides. This will have to be acute. There's no ambiguity there. That's by law of sines, and subtract to get the third angle. So now we can use law of cosines. So here we have angle A, side B, and side C. B equals 2, C equals 3, and here's A. We don't know what that is. So we have an angle, side, angle, side, SAS. So we want to use law of cosines to find, what does it say, the angle opposite the smallest side. That would have to be B. We're going to find angle B first. Find the side opposite the given angle first. We're going to find A first. So A squared equals B squared plus C squared minus 2BC cosine of A. So A squared is going to be equal to 2 squared plus 3 squared minus 2 times 3 cosine of 40 degrees. So A squared is going to be 13 minus 12 cosine 40 degrees. A squared is 3.807, so A must be 1.95. Now we can find angle B. Sine of 40 degrees over 1.95 equals sine of B over 2. Now given that this is 1.95 and that's 2, B is probably going to be somewhere close to 40 degrees. So sine of B is equal to 2 times sine of 40 degrees over 1.95. So B is going to be arc sine of 2 times sine 40 degrees over 1.95. B works out to be 41.21 degrees. Okay, now C is not so hard to find. It's just going to be 100 degrees, 180 degrees, minus 40 degrees plus 41.21 degrees. And C comes out to be 98.79 degrees. Those are the missing sides. Pen's getting kind of dry. I may have to go to a black pen here. Okay, feel free to pause that. We're going to next talk about solving a strategy for solving the side case. So in this case, we're going to find the angle opposite the longest side. This will take care of the obtuse angle if it's present. And we'll be guaranteed to get the proper angle. Oh, I should erase the board. We'll be guaranteed to get the proper angle because we're using law of cosines. It doesn't have the ambiguity. Because law of cosines produces angles from 0 to 180, so it can produce obtuse angles, whereas sine can't. Then either the remaining angles, find them, they'll be acute because the biggest angle was already found, so they have to be acute. So if the biggest angle was obtuse, it's already going to be found. Then find the third angle by subtracting. Okay, so here we have A equals 5, B equals 2, and C equals 6. So A is 5, little a is 5, little b is 2, little c is 6. So let's find an angle. We'll find the biggest angle first, and that's going to be C, because the side C is the biggest. So c squared equals a squared plus b squared minus 2bc cosine of c. So 6 squared equals 5 squared plus 2 squared minus 2 times 5, not 2bc, it's 2ab. 2 times 5 times 2 cosine of c. So the unknown here is the c. We want to find c. 36 equals, that's 25, and 4 is 29, minus 20 cosine c. Subtract the 29, we have 7 equals negative 20 cosine c. We'll divide by negative 20. And negative 7/20 equals cosine c. So c must be arc cosine of negative 7/20. And c comes out to be 110.49 degrees. That's an obtuse angle. Now we want to find, doesn't matter which one, I'm going to go for A. Sine of the 110.49 degrees over 6. I have to use that. I mean, we are going to have some error propagation because there's round off error in that. Don't have a lot of choice. We don't have any choice. Well, I guess we can go back and use law of cosines to find the others, but this arrow should be small enough it's not going to matter. Sine of A over 5. So sine of A is going to be equal to 5 times sine of 110.49 degrees over 6. So A is going to be arc sine of 5 times sine 110.49 degrees all over 6. And A comes out to be 51.32 degrees. So A is 51.32 degrees. Let's find B. B is going to be 180 degrees minus 110.49 degrees plus 51.32 degrees. So B is 18.19 degrees. Okay. Now we're going to get some really, I think that these two laws are great, but you get some extra great stuff today. For example, I'm going to erase this. Area of a triangle by using the sine formula. This is not a right triangle. Area of a triangle is 1/2 the product of the lengths of any two sides and the sine of their included angle. So area is either 1/2 AB sine C, 1/2 BC sine A, or 1/2 AC sine B. Another one, this one's my favorite. I love Heron's formula. Why? Because it is thousands of years old. It is from the Greek era. Given a triangle with sides A, B, and C, let S be A plus B plus C divided by 2. That's called the semiperimeter. Then the area is the square root of S times S minus A times S minus B times S minus C. Okay, find the area of the triangle using the following information. A is 131 degrees, B is 10, and C is 25. little b is 10, little c is 25. So you have two sides and the angle between them. So the area is going to be 1/2 times 25 times 10 times sine of 131 degrees. And the area is going to be 94.34 units squared. And if you just want that formula written again, it's 1/2, and we have b times, no, little b times c times sine A, capital A. Okay? Next one, I like this next problem. It might appear in a test, who knows? Bob wants to build an ice skating rink in his backyard. The land available is in the shape of a triangle with side lengths 20 feet, 23 feet, and 32 feet. So visualize it like this. 32 feet, 20 feet, 23 feet. So the question is, what is the area of the rink? How big, how much water is it going to need, you know, how much thick the ice and all that's going to matter, how much water, but also the area. So we'll use Heron's formula. First, the semi-perimeter is going to be 1/2 times 20 plus 23 plus 32. So the semi-perimeter is 37.5 feet. So the area is going to be the square root of 37.5 times 37.5 minus 23 times 37.5 minus 20 times 37.5 minus 32. So that's going to be the square root of 37.5 times 14.5 times 17.5 times 5.5. That's the square root of 52,335.938. So A would be 228.77 square feet. Okay. Again, feel free to pause. I'm going to scroll up. I prefer to use blue, but both these blues are kind of dim. Okay, next problem. A farmer puts a piece of fence across an inside corner of his barn to make a pen for his chickens. Excuse me, the lengths of the sides of the pen are to be 7 feet, 5 feet, and 8 feet. What are the respective angles? So here's a barn. Across one corner, he's going to be putting a piece of fence. And it's 5, 7, and 8. And we can't assume that this is a right angle here. It'd be nice if we could, but we can't. Well, let's just check that. 5 squared plus 7 squared. Is that equal to 8 squared? Is 25 plus 49 equal to 64? That's going to be 74. That's not 64. So, not a right triangle. Okay. So we're going to find, just out of this triangle, let's just draw it a little larger. No. 7, 8. So find angle B. I guess if we need to label things, here's B, Here's A, here's C. B would be the angle opposite the biggest side. We'll find B by using the law of cosines. So we'd have 8 squared equals 5 squared plus 7 squared minus 2 times 5 times 7 cosine of B. 64 equals, that's 74, minus 70 cosine B. So negative 10 equals negative 70 cosine B. So 1/7 is cosine B. So B would be arc cosine of 1/7. It's also called cosine inverse. So B would be 81.79 degrees. So I drew it up to, so it's actually acute. Now we can use law of sines to find another angle. I'll get, let's see, 7 is opposite the C. I'll get that C next. Actually, I'll go for A next. So sine of 81.79 degrees over 8 equals sine of A over 5. So 5 times sine of 81.79 degrees over 8 equals sine A. So arc sine 5 times sine of 81.79 degrees over 8 equals A. And I like to do this because I have the T89. I can put all that in there. I can see every piece. I can make sure it's right. And the nice thing is if I found sine of 81.79 first, wrote it down, and then put it in here, I'm going to have some error that I'm going to be propagating. So A would be 38.21 degrees. Therefore, C would be 180 degrees minus A is 38.21 degrees, and B is 81.79 degrees. C turns out to be 60 degrees. So the angles are 38.21 degrees, 81.79 degrees, and 60 degrees. Let's go to our last example for this section. Feel free to pause that one. Brittany and Jim are playing catch. They are standing 30 feet away from each other. Ryan went to join them and stands at a 50-degree angle away from Jim and a 70-degree angle away from Brittany. Drawing a picture of this is crucial for this one. Here's Brittany. Here's Jim. Ryan comes along. Now it says Ryan joins him 50-degree angle away from Jim. And then a 70-degree angle away from Brittany. So we can calculate what is the degree for Ryan, or R. R would equal 180 degrees minus 170 degrees plus 50 degrees, which is 60 degrees. We also know that Brittany and Jim are standing 30 feet away from each other. So how far is Ryan from Jim And how far is Ryan from Brittany? Well, we can use law of sines for this. Don't have to worry about law of cosines. So we'll call this side little b and little j. Okay, so sine of 60 degrees over 30, 60 over 30, sine 60 over 30, is equal to sine of 70 degrees over little b. So if we do flip both sides, 30 over sine 60 degrees equals b over sine 70 degrees. So b would be equal to 30 times sine 70 degrees over sine 60 degrees. And that's going to give us 32.55 feet. Okay. Now we'll go on to find J, the distance between Brittany and Ryan. 32.55 feet is the distance between Ryan and Jim, because that's the side opposite the angle for Brittany. So sine 60 degrees over 30 equals sine of 50 degrees over j, we called it. So we flip both sides, we have 30 over sine 60 degrees equals j over sine 50 degrees. So j would equal 30 times sine 50 degrees over sine 60 degrees. And j would be equal to 26.54 feet. Okay, so the way we'd read this, the distance Ryan is from Jim is 32.55 feet, and the distance Ryan is from Brittany is 26.54 feet. And that's the end of this section. Okay, thank you.